Okay, so we just performed the letterbox function that converted our IM0, our 768 by 1024 by 3 image, into IM, which is a 640 by 640 by 3 image, by shrinking it first and then adding padding to it, as we did in the previous video. Now here, we're just calling the transpose function that, as its name indicates, returns a tensor that is transposed. So we're going from the OpenCV image of shape HWC for height, width, and channels, and we're converting that to channels, height, and width. So channel was index 2, so now we put it in index 0, and then index 0 and 1, height and width, now are index 1 and 2, respectively. And then here, our input image was in BGR format for blue, green, and red channels, and now we want it in RGB format, so we're inverting the order of the channels so that we have RGB instead, and of course maintaining the values, but now in RGB order. So I run this, and of course IM has been modified, and now here we're calling this function that returns a contiguous array in memory. So we run that, and now we're going to return the path, which is our only image, the newly created image with the right dimensions and the right channel format, our original OpenCV image, this flag which is set to none because we're doing inference on a single image and not streaming, and the string that we previously created. And now when I run this, these 5 values that I just mentioned will be saved, and we will use them in this for loop. So you can see these values have been created here, for example, path. And now we're going to step into the first profile, which calculates the current time. So I have that time right here, and returns the time. And that will be stored in a start and then return. And that is used to keep track of the time. So I run this. And then here, as its name indicates, we're creating a tensor from an NumPy array, which is the current format of the image. And we're sending to our device, which is CPU. So now IM has been modified, and now it's a tensor and not an array. Here we have floating point 16 set to false. So we're going to continue using float 32. Here you can see that our data type coming from previous operations, in particular letterboxing, had an image of unsigned integer 8 or 8 bits per channel, ranged from 0 to 255 for the pixel values. Now we want it in a floating point format because we're going to divide by 255 in order to convert the current range to a range that is between 0 and 1. So in order to perform that operation properly, we're converting it to the right floating point and then dividing by 255. So here you'll see that the data type will change when I run this. And now the values have not changed, except we have decimals now. And now when I run this, we've divided the current values, in the case of the first pixels, from 114 now to 0.44. And then here we're checking if a tensor is 3-dimensional, which we can see that it is. So we'll step into this and we'll add a 4th dimension, which corresponds to the batch dimension. So you can see that our torch size went from 3 by 640 by 640 to now 1/4 dimension. We're not going to meet this condition, so we'll step over that. And now, given that we've concluded this first timer or profile, we're calculating the time again and subtracting or getting the delta of that time. And we're not using CUDA, so we'll step over that, calculate the time, and then dt right here has a value which is pretty large, but of course, we've been stepping into it. So in normal operation, you will see that the time is pretty fast. Now let's jump into the next section here. I'll step over this. This is the timer function again. And now here, given that we set visualize to true, and we did it right here, where the visualize argument, I added this default equals true in order to visualize the features of the neural net, as we'll see later. So given that this is true, we're going to add a path to store those feature maps. We'll be using the increment path function that we used previously when we, at the very beginning, created this exp folder inside detect. So we will run this function. We'll be creating another folder here in order to store and save the feature maps resulting of the forward pass through the neural network. We'll see a folder named Explorer created here to save those feature maps later. Given that we're not meeting this condition, we'll step over this. And now, model, which is our detect multi-backend class, we're going to feed in our image, our tensor, we have augment set to false, but visualize set to true. So when I step into this, I'll be feeding the image into the forward method of the detect multi-backend class. So let's take a peek first. Inside command.py, the detect multi-backend class with subclasses from nn.module natively will call the forward method. So we will come right here when I run that. And now here, we're just unpacking the shape of the tensor. Remember, it's right here, 1 by 3 by 640 by 640, and just save it into these variables. So I run that. Our tensor is in floating point 32, so we'll step over that. And we had previously set this to false when we initialized the class, so we'll step over that as well. And this is going to be true, so we'll step into this. And then self.model, well, self is the detect multi-backend class, and model is the detection model right here. And the detection model is inside YOLOv5. And when we run the previous function, we'll be stepping into the forward method of the detection model class. And given that we have visualized to true, we'll feed in this, otherwise we'll have just fed the model. So when I run that, we'll step right here. And here we are, augment is false, so we'll step over that. And now we're gonna call the self._forward ones method, which is not inside detection model, but because detection model inherits from base model, is inside base model right here. So we'll step into that, and now we're here.